Okay, so the first lesson was about when you have data that's not necessarily normal, the distribution, and you want to compare it to a claim. So we used the median, right, instead of the mean, and we compared the median by looking at the claim and then comparing all the data values to it. Remember when we did pluses and minuses and zero, okay? Today's is when you're comparing two. All right, so if you think about this, when you looked at means, you had one mean, that was a t-test. Then you compared two means, that's for independent. And then when it's dependent, remember you pair the data, so you would subtract them. Median's the same way, okay? So today is two medians for independent populations. So it's a non-parametric test that's used to determine if two independent population medians are equal. So if we're looking at population 1 compared to population 2, the median is the middle of the data. It's not pulled one way or the other like the mean is if you have like an outlier. And then again here and here. So if the null is that the mean is equal or less than or equal to, not the mean, excuse me, median, is equal to, less than, equal to, greater than or equal to, and the alternate is something else, like less than, greater than, or not equal to, would you think here we would reject the null, that they're equal? Scenario. Yes. We would definitely reject here, right? They're super far apart. What about on this one? So we might reject, we might fail to reject on this one. On this one, definitely fail to reject. Look how close they are, right? So it's probably not going to be statistically significant, that difference in the two medians, okay? So that's what this graphic is representing. So to run this non-parametric test, the test assigns ranks to the sample, okay? So the first thing you're going to do is arrange the values in increasing order. So you actually take the two samples, but you put it all together as one in order, okay? Once you put them in order, you assign ranks, starting with 1 and counting up. And then for any data values that are the same, you're going to change those ranks. I'll show you what that means with this first little baby example, okay? Instead of running the whole test on this one, we're just going to practice that. So for example, the heights of 10 fourth graders in inches are right here. Assign ranks to these values. So the first thing it does is says to arrange it in increasing order. So look through this list. What's the smallest value? 45. So I'm going to put that first. And then we have 46, 46. Actually, I have 3 46s. 46, 46, 46. That's okay. All right, and then 48. And then 49, 50, 52, 52. Thank you, sir. And then 54. Okay. So the preliminary rank is you just start counting at 1 and go up. So this would be 1, 2, 3, 4, 5, 6, 7, 8, 10, which makes sense because we have 10 data values, okay? However, when you have data values that are the same, which occurs here, 46, 46, 46, and here, 52 and 52, then you have to take those ranks and find the average, okay? So instead of being 2, this one's actually going to be 2 plus 3 plus 4, because those data values are the same. So I take those ranks and I add them and then divide by 3. That's how we find the average. So 2 plus 3 is 5, plus 4 is 9, 9 over 3 is 3. So these would all get the same rank of 3. All of these, you just bring down. Ranks aren't going to change. And then this one, 52 and 52 is the same. So 8 and 9, I would add 8 plus 9 and divide by 2, which gives me 8.5. So that's the final rank for these data values. So the rank sum test uses the mean and standard deviation to approximate the probability on a normal curve. So once you rank the data, it's called the rank sum test, right? Sum means what? So first we rank it, then we're going to be adding something, okay? So if you look here, what does this mean? Yeah, the mean. Okay, so this is the mean for the data once I rank it, the mean of the sums, okay? And then how do you figure this out? Well, what does n usually represent in statistics? Sample size. So because it's 2 independent sample sizes, you have 2 n's, okay? N sub 1 and n sub 2. So how do you figure out which one goes where? This is always the smaller of the 2. Okay? So n sub 1 is always going to be your smaller of the 2. With independent data, you don't have to have the same sample size. For dependent, you do, because you're pairing it. All right, so you would just take the smaller sample size, then times quantity, the smaller sample size plus the other sample size plus 1 divided by 2, okay? So then this formula is the standard deviation, okay? Which makes sense because normally we can find variance and then we square root it to get standard deviation, right? So this whole thing's square rooted. Again, you'll notice it uses the sample size, the 2 sample sizes, okay? Always divided by 12. This one's always divided by 2. So these formulas don't change ever, okay? So why do we do that? Well, because we can then standardize it and create a z-score from it and use the norm CDF key, okay? So your z formula is the mean, which we find using this, okay? Here, the standard deviation, which we find right there, it goes in the denominator. So what is this first piece, this S? The S is the sum of the ranks of the smaller. I don't want to say it like that. It's the smallest sum. You'll see in a second. So I should have just put smallest sum, the smaller sum. Okay. You can use norm CDF, which you find by going to second vars. So second vars, norm CDF, and you can find the p-value, okay? So remember, when you put in norm CDF, it asks you for the lower bound. So if your z-score is negative, then the lower bound is negative 10 to the 99. If it's a positive z-score and you're trying to find that upper tail, you have to put the z-score first, and then the upper limit is 10 to the 99. Do y'all remember that? And do you remember what your mean and standard deviation is if you're converting to a z-score? On the normal curve, if we convert and standardize, the mean becomes 0, and the standard deviation becomes 1. So this would be negative 1, that would be positive. So you just put in a 1 in your calculator, okay? So once you find the p-value, you can run any test, right? So the first thing we always do is write our hypothesis. So for this one, we would have mu sub 1 equals mu sub 2. What would my alternate be if that was my null? Doesn't equal. Now, if you put mu sub 1 is less than mu sub 2 here in the alternate, you can technically still have that as your null. right? Because the equal to always goes in the null. But I like it. It's a preference thing for me. If I put less than here, I make this one, instead of just equal to, I make it greater than or equal to. Have you seen that in your articles? Do they just use equal to, or do they normally have it like that? You finished with articles, everybody? They use weird letters. What were you saying? Most of yours just put equal. That's okay. Yeah, it's a preference thing.
Or sometimes it's just like instead of showing
Words. I think a lot of times people do that just because anyone can understand that, saying the means are not equal or the means are equal. Whereas when you use symbols, somebody might think M means mean, but really it's median. So, yeah. Okay, so first step, write your hypothesis, okay? Then you combine your two samples together from least to greatest, the values, and you assign overall ranks. Once you assign the overall ranks, you can then compute the mean, the standard deviation, and the z-score. Once we have the z-score, we can use the norm CDF function to compute our p-value. And then once we have our p-value, we can make a conclusion for our test. So let's jump right in. Example 1 says a sample of 14 students took a statistics class online, and another sample of 12 students took an equivalent class in a traditional classroom. Both classes were given the same final exam at the end of the course, and the scores were as follows. So this top row is my online students, those scores, and this bottom row is my traditional classroom scores, okay? So looking at this data, would you think it's independent or dependent? Because that's the thing, when you're learning something, they all belong to this lesson, right? But when you get a quiz or a test, or you have to figure out what tests run in real life, you have to identify as it independent or dependent. What, I'm sorry? Independent? Okay. Why? The online class doesn't affect the traditional class. The way I think about it is it's usually the same participants with like a pre-test, post-test if it's dependent, right? The same participants doing something multiple times maybe, right? So yeah, you're totally right. It does not affect it. Okay, so can you conclude that there is a difference between the median scores from the two classes? So if you had this raw data, you would make a histogram and look at it to see the distribution, right? And you would run the descriptive statistics and get the mean, the median, the standard deviation. You would do all that, right? So the first thing is, I know it's independent. I'm going to find those values for each of them. I'm going to make my graphical display for each of them, and I'm going to look at it. If we're looking at median, what's that tell me about the distribution? Normal, it's probably skewed, right? So that's why we would then run a test for medians instead of for means, okay? All right, so we're going to use a alpha level of 0.05. So the first thing you always do for your test is to state the hypothesis. So my null will be, and instead of 1, I put mu sub O for online. Write my alternate first. So what's your alternate going to be? Not equal to. So not mu. Gracious, I keep saying it. I'm sorry. Median, M sub O does not equal M sub T for traditional classroom, right? So then this one, M sub O does equal M sub T, okay? And just like the previous lesson where you've never had to subtract from 1, because you always use the lower sum and the lower sample sizes, you don't have to subtract from 1 again in this lesson. However, remember, if you have a 2-tailed test, you're only finding that lower tail, so what do you have to do to get the upper tail? Multiply by 2, and then that's your p-value, okay? All right, so the first thing we're going to do is order these, okay? So you have to put all this data together when you put them in order, okay? But you also have to tell me which category it belongs to. So I'm going to show you how to do that. So the lowest data value I see is 60. So I'm going to put a 60 right here. But then I'm also going to put that it belonged to the online category. The next one that I see is the smallest is 62. And it's also the online category, okay? Then I have 63, which belongs to the online group again. 64, which belongs to the traditional group. And I see another 64, which belongs to the traditional group. So does everybody see how to do this? Okay. Take a moment then to finish putting them in order, okay? And then I'll show you how to rank it in just a second. All right, so just double check with me. The next one I had was 70, and 72, 73, 74, 75, 77, 78, 78, 81, 82, 83, 84, 87, 89, 90, 90, 92, 97, 98, and 100. Okay? So something to point out, you'll notice there's multiple ones right here that have the same data value, okay? So I like to highlight it, and then in a minute I use another highlighter. So if you want to get those out, you don't have to do it, it's just, I'm just telling you. So like here and here, these 78s, I'm also going to highlight those ranks, so I make sure I give them the same rank. Then down here, the 90s. I think that's it, isn't it? Yeah. There's 3 groups that are the same, okay? And then, with that being said, these 64s were both T's. These 78s are both O's, you know, for online. But then down here, you have one's online and one's traditional. It doesn't matter because they get the same rank, okay? So when I was first going through this, I was like, ooh, what do you do? But it doesn't matter because, again, they get the same rank. So for mine, I had online because it was first and then traditional for those. So you do need to tell me the categories because that makes a difference in a second, okay? So these were both T's, and then I had T from 70 all the way down to 74. 75 is an O. 77 is a T. I already put that those are both O's, and then 81 is also an O down to 83. 84 was a T. 87 was an O. T. We had an O and a T for those. And then 92 is a T. 4 is an O. 97 is an O. 98 is an O. And 1. Alright, so the way that we rank it is we can go ahead and rank these based on the order, but anytime you have it highlighted, they're going to be the same rank. Okay? So I said 1, 2, 3, and then over here to the side I said 4, 5 there, 6, 7, 8, 9, 10, 11, and then again on the side 12, 13, 14, 15, 16, 17, 18, 19, on the side 20, 21, and then 22, 23, 24, 25, and 26. Should I have 26? Yes, because 14 and 12 makes 26 total, okay? All right, so then these, just like a while ago when we practiced, 4 plus 5 is 9 divided by 2 is 4.5. 12 plus 13 is 25 divided by 2 is 12.5. And 20 plus 21 divided by 2 is 20.5. So if you look, we can now find the two sums, okay? So you have to rank the data first, and then you find the sum for each one. So I'm going to find the sum for my online ranks and the sum for my traditional ranks. So that's why I use another highlighter. So right here, I went through and highlighted all the O's. So I highlighted right here between them, just so that's a T, so I don't need that. So all the O's I highlighted so I could add them together in just a second. So now that I've shown myself which ones, then I went through with my calculator and I said 1 plus 2 plus 3 plus 10 plus 12.5 plus 12.5 plus 14 plus 15 plus 16 plus 18 plus 20.5 plus 23 plus 24 plus 25. When you do that, you get your sum for your online ranks. So what did all of you get? 6.5. And now, all of these that I didn't put the green highlight, because it's the traditional, go through and add all those. What'd you get? $4.5 is what he said. Do you all agree? Yes? Okay. So look, team, which of those is smaller? 154. So I put an asterisk there just to help my brain. And then down here in this Z formula, I'm going to put 154.5 because that's smaller. All right? Go ahead and do it. So then we need our two sample sizes. So this is the number of data values for the online. So how many online did I have? 14. And then how many traditional? 12. Which of those is smaller? 12. So that's what goes on the outside here. So 12 times quantity, 12 plus, then I use the other one, so 14 plus 1, and then divided by 2. You get 162. So that is the mean of my ranked sums, okay? Now I can find my standard deviation. So I'm going to square root. And then again, I use 12 times 14 times quantity. 12 plus 14 plus 1, all divided by 12. You get about 19.442. Everybody? Okay, so once you have the mean, that's what you subtract from the smaller of the two sums. So it's going to be 154.5 minus 162, and then divided by that standard deviation, so 19.442. You get that it's about negative 0.39 z-score. Does it make sense that my z-score is negative? Yes, because that 154.5 is smaller than 162, so when you subtract, you get a negative, okay? All right, so to find the p-value, you're going to go to second vars. You're going to choose norm CDF. So this is a negative z-score, which is creating that lower tail, right? So I use what as my lower limit? Negative 10 to the 99. Then this z-score is my upper limit, so negative 0.39. Then my mean, when I standardize, is 0. And my standard deviation is 1. what do you get? .348, yeah. So is that the p-value? So you don't have to worry about left-tailed, right-tailed when you do this, just like in the previous lesson, but if it's a two-tailed test, you do have to take that and multiply by 2. So I have to take this value, multiply by 2, and I get 0. .697. Good. So now I take this, because that is my p-value right there, and I do my alpha. My alpha on this problem is 0.05. This is obviously greater than, so we fail to reject 2, the null. So which of these pictures then would probably be the representation of this scenario? The last one. Yeah. Very good. Okay. So fail to reject the null, which means there is not sufficient evidence. B. Y'all at the 0.05 level of significance to conclude yeah, I like to go back up there and read the question. Yes, to conclude that there is a difference median scores from the two classes. So I don't think this is difficult. I just think it's kind of time consuming, and you know, it's a lot of numbers to be typing in and stuff, so I feel like it's probably really easy to make a mistake, you know, so just try to double check. That's why I use highlighters too, because I want to make sure I'm actually adding the correct things. You don't have to though, okay? All right, let's look at example 2. Heart rates and beats per minute were measured for samples of 12 track athletes and 15 swimmers. The results are shown below. Can you conclude that the median heart rate is greater for swimmers than for track athletes? So, I know typically we write it, so we would say greater for swimmers, so swimmers greater than, but because you always have the smaller first, unless it forces you to do it, we typically write it for this unit, and I don't know why, but the only thing I can figure out, me and Miss Whitaker, is that because you use the smaller sum, you write that one first, okay? But that gets disproved on this one because of how it asks the question. So, back to this one though, we'll get there in a second. If I'm saying it's greater for swimmers, then which one would be smaller? So we're going to say the median for track is less than the median for swimmers. Which, you're still saying it's greater, but you're writing it with track first because it's smaller, okay? I wrote this one incorrectly based on how the book teaches it, so then it's like, wait a minute, why'd we do that? And the only thing we can figure is because you use a smaller sum, okay? But like I said, then the next example kind of disproves that, so... All right, so the median for track is less than the median for swimming, which means this one would be the median for track is equal to the median for swimming, or I could say greater than or equal to. All right, so you'll notice on this example and the next one, I gave it to you in order just to save a little bit of time. So then you only have to go through and find what category it belongs to, okay? So which one does 62 belong to? Track. 63? swim. 64, track, y'all agree? 65, track and swimming. I just put track first because it was listed first. Okay. 66, track and swimming. And then 68, 2 tracks. Good. 69, swimming. 70, track and swim. 71, swim. Good. 72, they're both. Let people get caught up. 75, 76, this track. 77, yep, those are both track heart rates. 78, swim. 79, $80, swim. 81, swim. 82, swim. A little faster as I go because I've crossed out so many, it helps. Everybody good? All right, now I do want to point out you don't have to do this again though, I just have to do what works for my brain. When I had 65 right here, and then I had 66 right here with it, I didn't highlight that the same color because then I felt like I would add all those ranks. Do you see how many are in a row are the same? So I actually switched colors. You don't have to do that. That's just a me thing to help my brain. And then it happens again down here. Somewhere. There it is. Yeah, the 72 and the 75s. So again, I switched colors because I didn't want to accidentally add all those ranks together. Okay. So usually we just go straight down, but on this one we got a lot that are the same, okay? So it would be, rank would be 1, 2, 3, then 4, 5. So what would these two be? 4.5. Okay, then these two, that's why I made them a different color, so I want to rank all these together. So this would be 6 and 7, which means these have a rank of 6.5. And then these would be 8 and 9, so 8.5. This one's 10, 11, 12, so 11.5. 13, 14, 15, so 14.5. 16, 17, 16.5. Okay. And this one would be 18, then 19, 20. So 19.5. 21, 22, 23. 2.5. Very good. There. 24, 25, 26, 27. Should I have 27? I had 12 for athletes and 15 for swimmers. Let me go ahead and write that up here. 12 for track athletes, track. 12 was track and 15 for swimmers. So then I went through and highlighted. Stop trying to talk while I write. I went through and highlighted all of my track ones. so I could add those. All right, what's your sum for track? Say it a little louder. Thank you. 129.5. And then your sum for swimmers? 248.5. So this is obviously smaller of the two, and then this one's smaller of the two. Okay? So now I can find, I'm going to go ahead and put that 129.5 down here actually for my sum. And then you can go ahead and find your mean and your standard deviation, okay? And then we'll all come back together. All right, so try to finish this one out. All right, so for this one, if I need to, I'll go in and write everything in. But did you get 168? Okay, when you rounded, did you get about 20.494 for the standard deviation? Okay. I love it. You are so great about answering me. Thank you for that. Truly. It is not fun as a teacher if you feel like you're just talking to yourself. All right, everybody good? Nobody needs to see it? Just make sure you use the smaller of the two for the sample size, okay? All right, so when we plug those values in, we get a z-score after you round of about negative 1.88. Okay? So then you go to second bars, norm CDF. And this is negative, right? So I'm going to keep that lower bound as negative 10 to the 99th power, then negative 1.88, then 0, then 1. And you get a value of 0.005, right? Yes. So I have to think of it that way, truly. If this is 0, right, and I get a z-score of negative 1.88, that's creating that tail. So if it's positive, it's up here, which is actually, that's not a tail, is it? So I would need to do 1 minus to get the tail. I'll just tell you though, you know, we've not taught non-parametric before this year, so I'm being honest about that. I don't think it's difficult. I've not worked any problems where I got a positive z-score. And I think it's because you always use the smaller rate. And then when you put it all together, your mean is bigger than it. So I don't anticipate that ever changing. But I didn't want to tell you it's never going to change just because I've not worked 100 examples. I mean, I don't know. So, okay. All right. So is this my p-value? Yes. So I'm going to compare it. On this one, what do we have? 0.05? Okay. That is less. So p is low. Reject the host. So reject the null. Okay. If my level had been 0.01, would I get a different result? Yes. Isn't that interesting? Okay. So you reject the null, which means there is sufficient evidence. I'm just going to read it. Is that okay? There is sufficient evidence at the 0.05 level of significance to conclude that the median heart rate is greater for swimmers than for track athletes. And I wrote it that way instead of the median heart rate for track athletes is less than, just because of how it was asked up there, okay? Any questions? All right. So one more example before the practice problems. And I feel like I can just, we can check stuff together, but I'm not necessarily going to go through this whole one. Is that okay? Because it's the same thing over and over. So gas mileages in miles per gallon were measured for samples of compact cars and mid-size cars. The results are as follows. So how many compact cars? We have 1, 2, 3, 4, 5 by 1, 2, 3. So my sample size for compact is 15. Size 2, 4, 6, 8, 10. Okay. So can you conclude that the median mileage is less for compact cars? So it's forcing what into my alternate? The less in. So I'm going to put compact cars first, even though if I look, that may not be the smaller sum. You know what I mean? But because of how the question is asked, I'm going to say median for compact is less than the median for midsize. Which this means that the null then will be equal to or greater than or equal to. Okay? You set those up. Do you feel confident? All right, everybody. I know you're still working, but I just want to verify the numbers for you. I'm going to write the sums up here so you can check your work with mine. And then you can let me know if you need to see anything.